I guess you can see that we're picking up here with question number 56 on our final exam review. We're talking about transformations. So here we're given a function f of x, and we want to graph this transformation. So we need to recognize that when the negative is with the x, this would be a horizontal flip. In other words, it flips across the y-axis. And this would be a vertical shift up 2 units. So if I take this graph and I would flip it across the axis, I can see what it would look like. And then I want to slide it up 2 units. So I think this would be our transformation. So we did a horizontal flip and then we slid it up 2 units. The next transformation has an order of operations. First it says add 2 to the x, so think what we would have to do. We would have to pick x 2 units smaller. So this is our horizontal shift, which is always in the opposite direction when it's a quantity inside the x parenthesis. So we're going to go left 2 units from the original, and then we're going to flip the y coordinates. So this would be a flip over the x-axis. So a vertical flip, in other words, because it changes the positive values to negative values. So let's take our original graph and we're going to slide it first 2 units to the left. So it would end up here, 2 units to the left. And then we're flipping that over the axis. So what used to be at +3 would now be at -3. And these values that were positive will now be negative. So that green graph should be the result. Okay, then we're going to graph some functions that you should know very easily. I think everyone understands now that f of x equals 3 is the same as y equals 3. And of course, you don't want to mix up horizontal lines with vertical lines. This might be easier if you thought of this in y equals mx plus b form. The slope is 1 and the y-intercept is 0. So this is our 45-degree line through the origin with a rise and run of 1. So we could plot, I guess it says that we're supposed to label some key points. I don't know that you have to label very many if it's very obvious. Absolute value of x. We know the absolute value of positive numbers stay positive, but so do the absolute value of negative numbers. So if you labeled a couple of points here, I think you would show your understanding. And then in graph D, we're doing transformations of C. So when we subtract 1 from x, we would have to shift it 1 unit to the right. So we would take our graph from C and we would go 1 unit to the right, and then I might think about what I want to do here. I don't want to close this. I just wanted to move that label, sorry. I wanted to label it up above. So far all I've done is 1 unit to the right, and then this is our vertical flip. So if you labeled that, we would have enough information. All right, and I'm gonna slide back to the next one. Think of the square root of x. This has a domain. We know that we can do the square root of 0, but we can't do square roots of negatives, so this would be our domain from 0 to infinity. The square root of 0 is 0. The square root of 1 is 1. We could go over to the square root of 4 is 2, and we know this is going to be a slow rising graph. And then in F, we're doing transformations. A negative inside the function is a horizontal flip. A negative outside the function is a vertical flip. And then this +2, which we could put behind the whole thing, this is going to shift it up 2 units. So perhaps you might like to do this one step at a time. So F is a transformation of E. So first if I did a horizontal flip, then if we did a vertical flip next, then we would be down here. And then we're taking this red graph and we're shifting it up 2 units. So our final answer, and it's eventually going to cross that axis, but what we know here is that this is at the point 0, 2. All right, the cube root of x, unlike the square root, the cube root of x, we can go from negative infinity to infinity because negative numbers also have cube roots. Think of negative 8, for example. At negative 8, the cube root is negative 2. And at positive 8, the cube root is positive 2. And at 0, the cube root is 0. So this is going to be this shape graph. And in h, instead of doing the cube root, we're cubing. Well, you could think of inverse functions. Remember that inverse functions fold over this 45-degree line? So hopefully you recognize the same shape as we got in letter G. But here we would be switching in the opposite direction, and maybe I could make it rise a little faster. So, oops, sorry, not doing too well here. So we recognize it as an inverse function because the x's and the y's trade places. So we could say that the cube function is the inverse of the cube root function. And then we've got some rational functions. This is the reciprocal function. So once you recognize that, you guys know what reciprocals are. Think if I started with 3, for example, the reciprocal of 3 is 1/3. The reciprocal of 1 is 1. The reciprocal of 1/3 is 3. So you should recognize what happens here, that we can't do the reciprocal of 0. So we know that we have to avoid division by 0. But the reciprocal of a very small number gets large, and the reciprocal of a very large number gets small. And then on the negative side, we have to finish. And this is another kind of hyperbola. So we also have, and I should keep the green color, sorry. The green, both of those green branches, because we know that we can do the reciprocal of the negative numbers as well. In B, we know we have to avoid division by 0. So there's our vertical asymptote at x equals 2. The degrees are equal, so we take the ratio of the leading coefficients. As x gets huge, the numerator is going to be about 3 times the size of the denominator. So remember our horizontal asymptote. When the degrees are equal, we take the ratio of the leading coefficients. So there's our horizontal asymptote. And if we let x be 0, we know this is going to give us a value of 0 over negative 2. So we know we're going to have a graph down here. And if you're in doubt, try putting the number 3 in for x, and you'll see that you get 9 over 1. So we're going to be up here for our graph in letter B. In C, this denominator is factorable, x minus 2, x plus 2. So you can see that we get 2 vertical asymptotes at x equals 2 and at x equals negative 2. We can see the degree of the denominator is larger. So when x gets large, the denominator is growing faster than the numerator. So if you think about a fraction where the denominator gets really large, like 100 over 10,000, it gets closer and closer to 0. When the degree of the denominator is larger, then y equals 0 is our horizontal asymptote. If we put 0 in for x, we get a y-intercept of negative 1/4. And if we set the numerator equal to 0, then we'll be finding our other intercept here. So at negative 1 for x, y will be equal to 0. And we could try putting in a value of 1 for x to see what happens. If x is 1, we would get 2 over negative 3. So we can see the shape. These graphs in the center could all be different. And what should we do on the outside? We should try a number. Let's put 3 in for x. We would get 4 over 9 minus 4 is 5. So we would get a positive 4/5. So it's going to be above the axis. And if we put negative 3 in for x, we'd get negative 2 over 5. So there we can see it's going to be below the axis. And again, you don't have to be very precise for these, but I should label here. I did know my intercepts, so we should label those intercepts clearly. Okay, and I think we can do piecewise functions here in this video as well. It's really just putting two graphs with separate domains and then putting them together on the same axis. So when x is less than 1, we want to graph this line. When x is less than 1, well, this line, because f of x is of course y equals, so that would have a y-intercept of 1, and it has a slope of 2, rise 2, run 1, and I would do an open circle here, because when x is equal to 1, this is not included in this domain. And then when x is between 1 and 5, 2, 3, 4, 5, when x is between 1 and 5 inclusive, y is equal to 4. So here we would do a solid circle and a horizontal segment, and because of the equal sign here, that's why I'm doing solid circles, because those endpoints are included. If it said x is less than 5, then I would have left it as an empty circle. Okay, so b is a piecewise defined function. It's just 3 separate pieces of the domain. So when x is negative, less than 0, we've got our parabola, x squared. So I'm going to do an open circle, and that negative half of the parabola. When x is between 0 and 1, we've got a straight line with a y-intercept of 2 and a slope of 1. So we're going to go up 1 square over 1 square. So here we're going to get a piece of a line, and I should label these axes so you can see where we are. And then when x is greater than 1, we do this square root function slid up 2 units. So think what the square root function is. I'm going to draw that as a dotted segment, and then I'm going to slide it up. So I only want this square root function starting at 1. So think what would happen here if we put 1 into x. We would start out at 3. So this graph slid up, and notice that it fills in, it connects right to that circle. So a piecewise defined function, sometimes it has discontinuities where it jumps from one point to another, and sometimes by coincidence the two pieces of the function pick up right where the other piece left off. Okay, and we've got one more quick question about 59. The domain of this function, this arrow goes forever because it says x less than 1, but this part of the function says we stop at 5. So our domain is negative infinity to 5, and then we do a square bracket because the 5 is included. For the range of that function, what did we come up with? This branch starts at 3 and goes down forever. So negative infinity to 3 for one branch. And then that's also union with the other branch. Oops, nope, the other branch is not 3, it is 4. Is there another way to write this in set builder? Sure. The set of all y such that y is less than or equal to 3 or y is equal to 4. So you can either use interval notation or you can use set builder notation.